Okay, so anyone doesn't know already, my name is Jonas Wall, and I work as a teacher in a secondary school in Sweden, and I also administer the Swedish GeoGebra Institute. I'm going to talk now about something strange called Jackknife resampling. A jackknife is one of these like Swiss Army tools that you fold out, that is always useful and you have it always handy. And resampling is a statistical tool or method. And let's start with what does this mean? Statistics is, to me, one of these subjects that isn't math. It's something else, and they use strange signs which are hard to decipher, and I always have to go it's the average. So it was a little bit difficult to decipher this, but resampling methods are when you have a large data set, maybe you have population data or something, and instead of doing statistics on the entirety of the material, you take a sample of the material, but you also resample it. You take many different samples and then you do the statistics on these samples. Jackknife resampling is the most minor version of this, and it works even for small data sets, and using it we can with quite little effort find statistics like what I'm after in this case. I want to find the errors of parameters that have been determined by fitting functions to data points in GeoGebra. So like if you fit a straight line, you get ax plus b, then you get the values for a and the value for b, but you don't get the errors. You don't get an estimate of how big errors are in those values. And this is something that as a physics teacher, I've been annoyed at GeoGebra not doing this. But finally I found a way. Hint, hint, Marcus, but he's not here. So here's a typical physics experiment. We do this in physics 1. We take a pendulum, and just like Galilei noticed that when he was sitting in church and the wind was blowing the chandeliers in the ceiling, the ones with the longer lines, they had a longer period, and the ones with shorter lines have short periods. And there's a theoretical formula for this. The period, the time it takes to swing back and forth, is 2 pi times the root of the length of the string divided by the acceleration due to gravity. And you can rewrite that so that you get all the constants in one section here multiplied by the square root of the distance. And then you do the experiment. You take data points, you put them into GeoGebra, you do the spreadsheet. If you do the spreadsheet, you select the values and you right click and you go create a list of points, and then you do a fit to a function, and in this case you have to have a special function like k2 times the root of d, and you find the value 1.9945, and then you work out from that what the value of g is. And in this particular case, this is an almost randomly chosen lab group I had this spring. They got the best result. And now 9.92, you know it should be somewhere around 9.82. So how big is the error? Is this within the error margin? Is 9.82 within the error margin for this value? We don't know. Unless we actually do Jackknife resampling. And this is how you do that. You remove one data point at a time. So if I have, in this case, 8 data points, but I stole the picture from somewhere else and they have 10 data points. So you have 10 data points, you remove one, and you do the calculation with the remaining 9 values. So you get a value for G is something. Then you put that data point back and you remove another one. And you still have 9 points to work with, but now you get a slightly different value of G. You repeat this for every data point, and in the end you have 10 values of G if you had 10 data points. You've removed each one time. So this is resampling your original data. And then we can do things like calculate standard deviations. Let's just recap statistics for normal distributed material. Typically we say that errors due to measurement are normally normal distributed. But there's a sort of shortcut we always make. We always talk about standard deviation, but there's actually something called the standard error for any type of distribution. And for normally distributed data, the standard error is equal to the standard deviation. And if you want 95% confidence values, well, first you multiply by 1.96, the magic number. But then this is the size of the interval for a new data point being measured. For the mean, you also divide by the square root of the number of measurements. But since we don't need the standard error, we'd never talk about it. We only talk about the standard deviation. Now there is a little quirk here for this method. The standard error is not the standard deviation. It is the standard deviation times the root of the number of estimates times this factor n over n minus 1. Now, n over n minus 1 is always just sort of almost 1. And we're doing estimates of errors. Right, come on. Let's just drop that factor. Doesn't matter if we wind up with, you know, an error size which is like 10%, especially not at secondary school. So let's say that the standard error is this standard deviation times root n. But that means that the 95% confidence interval of the mean is s times the root n, because that's the standard error, and then divided by the root n, so it's just 1.96 times s. So if you haven't talked about standard deviation of the mean, you don't really need to. You can just say, oh, multiply by the magic number. It will work. So I've done this in class, especially one class, which I've done it 3 times. And the first time was difficult, and they had pretty good instructions, but they still needed hands-on help when they were doing it. And when we summarized it afterwards, there were lots and lots of, ooh, is that what we were doing? The second time went smoother, and the third time it was like, oh, this guy is never going to stop, is he? We better learn this. And I found it very useful to say that, this is something you will do every time you do a lab from here forth on. Because that made them sort of determined to, really actually learn it. I've done some simulations, and the correct way of doing this is to take the covariance matrix, which is a name I've heard, which is also something you can calculate from a fit. And you take the diagonal elements and you square them, and that is the errors of the parameters. Okay, fine. I almost understood that. And there is, GeoGebra doesn't produce this covariance matrix, but SciPy, the SciPy module in Python does. So I ran some programs. So let's have a look at these. So here is a typical Python program in REPL-IT, which is an online place where you can store programs and run them. And what I do is I just have 8 points which I made up. Completely non-interesting data. It's just for something. And then I produce these Jackknife lists, and I calculate in 2 ways this error, the Jackknife way and the covariance matrix way. So let's just run that and see what happens. And so here's a little image showing that, these are the like 8 different lines that are produced. So you can actually see roughly what happens with the parameters. And then I tried to make output that would be legible. So it's determined that the parameter values are, and that the standard errors are, and the 95% confidence level sizes are, and this is using the standard method. And so we get these values for the parameters, 1.4 plus minus 0.12. Jackknife method produces a lot of values, and they have maximum and minimum values and averages and standard deviation, and produce basically the same result, 1.4 plus minus 0.12 for the first parameter. And at the bottom I calculate, I should try and get rid of that. I calculate that the factor between the error for the Jackknife and the error for the normal. And for one of the parameters it's like 1, and for the other parameters it's 0.7. So you think, oh, that's not very good. Same ballpark, but wrong goal. So I try some other data. I try randomized data. So I have here a line which should be 0.5 times x plus 2. But I then randomize it and add something to it. I can't remember how much I add now. Well, we'll see. And basically we get the same output. This time a little more back and forth because of the randomization. This time I got 0.73 and 0.8 at the bottom. Not very good. Let's run it again. This time I got 0.82 and 1.06. So it's from time to time it varies a bit. But then of course I put all that in an extra loop and I did like 1,000 times. And we shall see where it lands. This typically takes a couple of seconds. And over 1,000 runs, it's pretty good. It's like 1.5% wrong with one of the parameters and 7-ish% wrong with the other parameter. And this is a method that the students actually see what they're doing. It's not just let us write a program and call this black box and we will get the errors. It's actually something that they've done from scratch. They've actually done standard deviation once by hand, so they know how it's done. So I quite like this method of doing it. And this was like, 0.5x plus 2. If I'd chosen different values or a different type of fit, maybe this would be different, but I haven't had time to do that. But it's in the right ballpark. It's something that you can do and show the students. And then I thought I had this great idea to measure how big the errors would be, depending on the size of the random variable that I added. And they're roughly linear, so yeah, it's obvious. The bigger the errors, the bigger the intervals. So that wasn't very interesting. We've got lots of links. I've got a folder containing materials. I've got a GeoGebra book with constructions. I've got screencasts in Swedish and English showing this method. I've got the Python programs, and there's even a reference to some sort of text which has got lots of sum signs in it. Any questions?
How much time did it take you to do it the first time? Like, did you plan ahead? Like, I will spend. Like you said, it was tricky.
It was even more than tricky.
Yeah.
I had to write the full instructions for the students, and to do that I had to be clear in my mind what I did. And by that time, I hadn't yet discovered that little detail about multiplying by root n. So we got results that were ridiculously small, and we thought, wow, these are very good values. And then, of course, the second time I had to go back and say, well, we actually did it wrong the first time. We should do this. So it was a fair amount of work, but it was fun. It was something I've always wanted to do ever since I started to do regressions and fits in GeoGebra for physics. Why can't I have the size of the errors? Yeah.
Maybe you said, but is it the RMSE error, the root mean square error? Or is it something?
No, it's something else, I think. RMS, root mean square, that's... I don't know. This is statistics.
I use physical program Capstone.
Yeah. Yeah.
You always get the root mean square error.
Yeah, that's very nice of them.
It's the same.
Could be. I haven't got a clue. This is an approximation to get the squares on the diagonal elements of the covariance matrix. I learned that by heart. Yeah.
What is usually the first project you introduce to your students? Like, is it taking parameters of a straight line, or
in physics? Yeah, it's, you know, we are going to do a lab, and this is how we do labs. We measure things, typically 2 things at a time. We make points, we make a fit, and then we draw conclusions from like the slope of a line or something. Okay. So this is like what I always do in physics labs. Okay, so they're very used to doing regressions and fitting functions to data points. Mm-hmm. They've already done that a lot of times. So this was just the addition of the error estimation. Yeah.
And something that's irritating in GeoGebra, when you do a nonlinear regression, you get the R value in the
which is completely nonsensical. Yes. R is just valid for linear. Yeah. But it's like they did the statistics bit a long time ago, and it works. Do not touch things that work. Yeah. I mean, you can calculate it, but it doesn't really mean anything. Yeah, possibly. Yeah. We've got masses of time. Do you know how to do fits for non-standard functions, like a constant times the root of d? Shall I show you? Okay. So let's start GeoGebra. And you really need to do this in Classic if you do it my way, because I use the spreadsheet. So we've measured something. Wow, these are really good values. And let's say we have something like this. Oops. So we select them, right click, create list of points. I should change to English. And then let's see what we have. And then in order to do a non-standard, I can do a fit linear or something like that. Fit line, for instance. And the list name is L1 in Swedish. But that doesn't really work. So you realize that, okay, so I need to do a square root. And I want it to be a square root. I don't want to do just an ordinary power fit. So then I produce a special function which you can call anything, but I always call it m of x because it's my model function and it should contain sliders. So I will say, okay, this is a constant times the root of x. And that can look just like that. And if I change the slider, I could make it look more or less like my data, but it doesn't really matter. It's useful if it's roughly similar, because it's the starting point for the algorithm to find the actual value later. But I can just as well hide it. But by doing this, I can now refer to it. So the command is fit, just fit. My list of points, which is L1, find a function of type m. And so you can do any kind of function. This is very useful. Right, I'm finished.
Thank you.
Thank you.